We start with a standard mathematical expression, 9 minus 5 plus 2. It immediately snaps into its postfix equivalent, 9 5 minus 2 plus. A compiler's parser can easily read the first expression and confirm that the sequence of digits and operators is grammatically valid. But confirming a sentence follows the rules of grammar is different from understanding its purpose. The parser identifies the hierarchy of the code, but the structural arrangement alone does not provide executable meaning. It knows that a minus sign sits between a 9 and a 5, but the syntax rules do not describe how to perform the actual mathematical translation. To cross this gap, compilers rely on a mechanism known as syntax-directed translation. Syntax analysis provides the structural route, but a compiler requires a systematic way to map executable semantics onto that established structure. This block diagram shows the high-level architecture of a compiler's front end. The Syntax-Semantics Bridge sits specifically right here, in the transition phase between the syntax analyzer and the intermediate code generator. The foundational theory for this architecture is thoroughly detailed in the classic text, Compilers, Principles, Techniques, and Tools. We will use the translation of standard infix math into postfix notation as a micromodel. By tracking how a system translates a few numbers, we can expose exactly how a compiler understands code. The exact same mechanics used to process simple arithmetic are scaled up to compile thousands of lines of complex software. Here are the context-free grammar rules for expressions, terms, and digits. Reading 9 minus 5 plus 2, the parser constructs a hierarchical parse tree. The tree's nodes structurally enforce the correct order of operations, physically separating subtraction from addition. At this stage, the tree contains no data regarding the output sequence. It represents the shape of the expression, but not its translation. The parse tree defines the route of execution, but requires injected data to produce the results of that execution. This syntax-directed definition, or SDD, attaches semantic rules to our grammar. We define attribute T to hold the postfix notation. Leaf notes populate with base values, 9, 5, 2. These flow upward, concatenating step by step until the root achieves the final translation, 9, 5 minus 2 plus. This specific behavior relies on what we call a synthesized attribute. It means a parent node's meaning is derived entirely from its offspring. Because the data only flows upward, the entire tree can be resolved in a single bottom-up pass. Synthesized attributes reduce complex linguistic translations into simple local operations between a parent and its direct children. But how does a computer systematically navigate this spatial structure in memory to compute those attributes? A dashed line traces a depth-first traversal, diving recursively down the extreme left branch. Passing down, it simply visits nodes to establish the root without evaluating them. Computation triggers strictly during the post-order phase on the way up, precisely when returning to a parent. This spatial geometry and post-order traversal naturally forces the compiler to respect the correct order of operations without human intervention. Building a parse tree for short math is trivial, but for massive software programs, building massive trees and storing concatenated strings introduces significant memory overhead. The translation scheme, or SDT, allows us to generate output incrementally without storing data in memory. We achieve this by embedding semantic actions, these program fragments inside curly braces, directly into the grammar rules, specifically placed at the extreme right of the productions. Placing these actions at the end of a production perfectly synchronizes their execution with the exact moment a post-order traversal leaves that specific node. An SDT bypasses the physical tree entirely. By executing actions sequentially, the compiler emits the translated postfix string character by character on the fly. This split screen contrasts two frameworks, the syntax-directed definition on the left and the translation scheme on the right. The SDD is the declarative specification, outlining what the rules are. The SDT is the procedural implementation, dictating how and when those rules execute. This decoupling is critical for compiler engineers. It allows them to design the logic of a language independently from the memory constraints of the machine compiling it. Here we generated a simple postfix string, but modern compilers rely on this exact framework of attributes to manage static type checking, track memory, and build highly complex intermediate representations. By embedding semantic logic into the structural grammar, the compiler creates a direct link between the syntax of a language and its intended meaning.